what better speakers to initiate this partnership between the mathematicians and the computer scientists than Simon Peyton Jones and Andy Gordon. So it's my great pleasure to introduce these. Simon is a computer scientist who specializes in functional programming languages, and he's most well known for being one of the designers of Haskell and a lead developer of Glasgow Haskell Compiler. So Simon currently works at Microsoft as a senior principal researcher. He has also been heavily involved with advocating computer education reform, and he is the chair of computing at school. So those of you who don't know, Simon is from Trinity College, Cambridge.
We'd also like to welcome Professor Andy Gordon, who is also a computer scientist at Microsoft Research, as well as being a part-time professor at the University of Edinburgh. He studied for his PhD at King's in Cambridge before working at the computer lab here. His research now focuses on programming languages, and in particular working to develop Microsoft Excel as a programming language.
Shall we kick off?
Yes, let's go.
Yeah, good. And David Culver, is this David Culver from F9? Was it F9? I came to see years ago, who's a true Excel expert.
David Culver here, yes, from Operas.
Operas, yes.
Absolutely.
Wow. Oh, so okay. So you folks, you are in the presence of a true Excel expert before whom I bow. This man uses Excel like other people use pianos. Okay. So Excel meets Lambda. So Zach said that not all of you might be expert functional programmers. So I thought we'd start with a quick skate through what is functional programming and why might it be important. So here we go. You will all have heard of Turing machines, right? So famously invented by Alan Turing, and it's a very imperative kind of thing. A Turing machine modifies these, ones and zeros on a tape. It has a rewrite head, moves the tape left and right. It modifies the number on the tape. It has a state at any moment. It's a very stateful kind of thing. But at the same time that Alan Turing was thinking all this, Alonzo Church in America was dreaming up the Lambda calculus. So here is the Lambda calculus. I'm going to say a little bit more about it. Lambda calculus is a little programming language. It only has three syntactic forms: variables, applications, and this form lambda x.e. So the x is a variable and the e is just another term. So I hope you see the BNF on the screen right at the moment. And it only has one computation rule. If you apply a lambda to an argument here, e2, all you do is you take the body of the lambda, e1, and you substitute e2 for x inside e1. I'm going to show you that in action in a second. Notice this was done about the same time. There's Alan Turing 1936, Alonzo Church in 1935. In fact, Alonzo Church published his paper about the Lambda calculus just as Turing was finishing a paper about the Turing machine, and Turing hurriedly added an appendix to his paper to explain the connection between the two, which is something about what we'll talk about. So here is the, Turing then immediately went to Princeton and said, Alonzo Church, can I be your student? And he actually worked at Princeton as Church's student for some time. Now, here's how the Lambda calculus works. In mathematics, we might conventionally say, let f be a function defined by f of x equals x plus 7. So we give function names and then we define their behavior. In Lambda calculus, we just work without the names a lot of the time. So lambda x, x plus 7 is the function of x that adds 7 to its argument. That's the way to think of it. So it is lambda x means it's a function, its argument is x, and to apply the function, you simply substitute the argument for x. So here's a concrete example in the blue boxes at the top is a lambda term. It's lambda x dot x applied to lambda y plus 7 applied to 3. Okay, and I can evaluate this term in more than one way. Going down and to the right, what have I done? I've applied that first lambda x dot x, and I've substituted for x inside lambda x dot x. What have I substituted? Oh, the term on the right. So I just get lambda y plus 7 applied to 3. And then I could evaluate that, but I substitute 3 for y and get 3 plus 7, and then I add them and get 10. But if I did it the other way, I could have said, let's leave the lambda x alone and just do some evaluation inside its argument. So here, lambda y plus 7 applied to 3, substitute 3 for y, so I get 3 plus 7, and then I can either do the outer lambda, or I can turn the 3 plus 7 into 10. Either way, I get to 10. So you can see there's a sort of multiple ways in which you can evaluate a lambda term. It feels quite different to your Turing machine. It really doesn't feel like the same thing at all, in fact. But it does feels closer to mathematics, I think, because it's just working with functions. Now, I've used numbers in this slide, right, with 3s and 7s and so forth. But Church didn't have numbers to begin with. He said, how little can we get away with? What about just variables applications and lambdas? And he noticed that we can model numbers. So he wrote down these terms. I've written them 1, 2, 3, and it's just lambda x, lambda x, f applied to x, f applied to f of x, f. So the number of applications of f, that's the number that I've written on the left. And so now I got a set of lambda terms and a set of numbers. I put them in one-to-one correspondence, right? So for every number, I can cough up a lambda term. A lambda term of that form corresponds to a number. And then it turns out that if you regard numbers like this, you can add them very simply. Here is a lambda term called add here, which will add to such numbers. So n1 and n2 are going to be these numbers. I might apply this whole thing to 2 and 3, for example. And then it's got to return a number. So it takes 2 numbers and returns numbers. All numbers here take 2 arguments, f and an x. There's the f and the x. And I'm not going to work through this because that would take the whole time. I just want to say that if you can imagine if we compose something that applies f to its argument twice with something that applies f to its argument 3 times, you get something that applies f to its argument 5 times. That's addition, right, in this funny world, right? So Church said, well, we can add numbers. And then he worked out that you could multiply numbers too. And I'm absolutely not going to go through this, but when you see the slides afterwards, I encourage you to work it out. But I've told you already everything you need to know to evaluate lambda terms that are multiplying numbers. But then there was a puzzle. Could I subtract? If I could subtract as well, then I can do all of arithmetic with x, e1 applied to e2, and lambda x dot e. That's pretty powerful, right? But it doesn't seem that I could subtract. How could I unapply f? Well, they had a buddy called Cleany, and he went to the dentist. And while he was at the dentist, he had an idea for how you could subtract 1. And here is the lambda term for subtracting 1 from one of these numbers. It's a little bit more complicated. I'm definitely not going to tell you about it, but it's pretty amazing that it could be done at all. And so now they found you could do all of arithmetic with pure lambda calculus. So then they said, oh, but maybe that means that lambda calculus. So now we got the idea that let's say, we rapidly got to this picture. A Turing machine can compute things, and Turing's point was, let's define computability, what it means for a computer to be able to do something by the things a Turing machine can compute. And any other computer can compute exactly the same things. It was his hypothesis, right? Now then, Church had come up with this completely different idea for how you might calculate, using symbol pushing and some mechanical arrangements. And so now we have a collection of things that the lambda calculus can compute. But they very rapidly worked out, in fact, it was in Turing's appendix, that these two things are the same. That is, despite their very different roots, they can compute exactly the same collection of things. So this was, as it were, almost evidence that the idea of things that are computable was a well-defined notion, because it seemed that however you defined computability, it came out to the same set of things. So that was very remarkable, I think, very remarkable. So that then, and another way to then retrospectively reconstruct history then, is that from Turing machines grew imperative programming. We'll say a bit more about that. From lambda calculus grew functional programming, but they're all forms of programming and they can all program the same things. So in fact, imperative programming has become wildly dominant. Functional programming has been, until recently, just a pinprick, but more of that anon, because it has been the story of my professional life. Let's just talk a little bit about programming. So here is Euclid's algorithm for extracting the GCD of two numbers, and he described it in some steps. To take the GCD of A and B, if A is smaller than B, and exchange them, so now A is bigger, right? If B is 0, the result is A. If not, divide A by B, giving remainder R. Replace A by B and B by R, and start again at step 2. So here's a little picture, right, that you might say A and B are 9 and 15. You first of all swap them. That was step 1. Step 2 is you take the remainder. So the remainder is in column 3 here, headed R. The remainder is 6. Then you replace A by B, so it becomes 9 in step 4 of the little table. And B becomes R, that's step 6. And then you repeat the exercise. Take the remainder when you divide A by R, that's 3, and then shift. Take the remainder, and soon you get to 0. Now you found the GCD. This is Euclid's algorithm for finding GCD. Now, you can write this out as a sequence of steps and sort of locations that change their value over time. And you get a program that looks like this. This is a sort of, this is in C or something very like it. And you've got variables called high and low, and they change their values over time, and you can reason about the correctness of this thing. And well, this is imperative programming. It's very sequential. It has control flow. It has for loops. It has while loops. It has conditionals, and so forth. Now, oh, and crucially, it has mutable locations. High and low are not the names of values, they're the names of locations that contain values. But you could also do the same thing, let's see, with a spreadsheet. So here I've taken that table that I showed you here, and I've just turned it into a spreadsheet with successive rows. And here are the formulae in the successive rows. Now, this works fine, and it can compute GCDs, and I haven't mutated anything now. I've just used pure functions and data flow to do this. But of course, the number of rows in the spreadsheet would need to grow if I wanted to take the GCD of bigger numbers. But at least there's no sequence of steps, or order is driven, evaluation is driven by essentially data dependency. But the fact is that in Excel, you need to change the number of steps. Well, another thing you could do would be to switch to a more grown-up functional programming language, like, let's say, Haskell. So here is GCD in Haskell. And this now really looks like mathematics. I'd like you to think of functional programming as mathematics made incarnate. It's just maths made executable. So this says the GCD of A and B, the vertical bar means if, or in a case, or in case A is less than B, take the GCD of B and A. If B is equal to 0, the result is A. Otherwise, take the GCD of B and A mod B, right? What could be simpler than that? It kind of, I think this is much easier to understand than the imperative program on the left, but I'm biased. But I just want to give you a flavor of what functional programming is about. But I do want to stress that in the functional programming stuff, the execution model is that one that I showed you of reducing lambda terms. The lambda terms really are the execution model of the functional program, and it's sort of inherently parallel in a way that imperative programming is inherently sequential. And moreover, functional programming always has immutable values, whereas imperative programming tends to program with mutable locations. I personally like functional programming, but I just want to, at least I want you to get the sense of that functional programs are at least a completely different way of thinking about the whole exercise of programming. All right, now, a quick last piece that I'm not going to go into in any depth, but I wanted to show you this because you are mathematicians, or some of you are mathematicians. Read this excellent paper by Phil Wadler called Propositions as Types. It explores something called the Hurry-Howard isomorphism. So also around the same time, incredibly fertile time, 1934, Curry observed that every type of a function, A arrow B, so if you think of functions out having a type from A to B, that you can be read as an implication or proposition, A implies B. And in fact, if you write out the rules of logic, that's in the top left-hand diagram here, the rules of logic for and or and implication in natural deduction, and then you write out the typing judgments for typed lambda calculus. I hope you can intuitively guess what typed lambda calculus might look like. They are the same, right? The blue bits of these two pictures are identical. The red bits are the lambda terms. So in a very real and deep sense, a type you can think of as a proposition, and a lambda term you can think of, a lambda term with that type is a proof of that proposition. That is a very deep statement. It's called the Curry-Howard isomorphism, and it has ramifications all over functional programming. It's just amazing. So if you've not heard about it, go read about it. Read Phil's paper. It's very good reading. So much by way of a quick introduction. Now, I'm going to skip this. I want to move back towards Excel and Microsoft. I joined, except that nobody's asked a question. I'm going to go on anyway, but I do encourage you to interrupt. I joined Microsoft in 1998, 22 years ago. And the first thought I had was, what on earth is a functional programmer? How am I going to have any impact in a company like Microsoft? Maybe there's some teeny weeny little corner of Microsoft that does functional programming. Let me seek it out. But then I realized there's not just a teeny weeny corner. There's a huge business in Microsoft called Excel, whose core computational model is functional programming. I've already shown you that. So the idea that I started to explore was, let's look at Excel through a functional programming lens don't think of it just as a business modeling tool, right? It is a business modeling tool, you know, tables of numbers, charts, visualization, sorting, pivot tables. And by the way, there are formulae. Instead, let's look at that by the way part and say, what would it mean to really focus attention on that bit, right? Because that is, after all, functional programming in a product that used by more people in the world write formulae in Excel than write C# and C++ and C programs altogether. Of course, we're not the only people to have had this idea, right? Verlina Hermans. Go and read papers by Verlina Hermans and listen to her talk. She's an excellent speaker. And her point, which is the same as ours, is that really ambitious spreadsheets have thousands of formulae. So by any standards, they are programs. They're developed over years. They're huge assets that people care about a lot. They are very complicated, purely functional programs. So the question becomes, how could we do better? And the answers are incredibly simple because we have lots of experience of functional programming, and the Excel hasn't sort of been scaled up as a language at all. So, but before thinking what we could do to make Excel more like traditional functional programming languages, let's just look at how Excel differs from ordinary programming, right? So in the left-hand column, traditional programming, in the right-hand column, Excel. Traditional programming, professional programmers looking mainly at the code. In Excel, end-user domain experts who just don't think of themselves as programmers at all, who look mainly at the data. The code is kind of invisible in those formulae, right? Traditional programming, you have this edit, compile, run cycle, but in a spreadsheet, it's always live. Every time you do a keystroke, practically, as soon as you finish the formula, blam, the spreadsheet recalculates. And in traditional imperative programming, the program evolves over time. It executes in time. Mutable values change their value. But in Excel, programmers are laid out in space. But it's a rather weak programming language as well. In traditional programming, we have rich data, arrays and records, and nested data structures. In Excel, really, you only have scalar data. And in traditional programming languages, you can define new functions. In fact, we do that all the time. Define new functions and new procedures. In Excel, no dice, right? You've got a fixed library of 600 odd functions, and that's what you can use. So how could we do better? How could we do better? Well, let's focus on doing better on these two particular axes. Maybe we could have ways of adding user-defined functions in Excel, defined not by writing these new functions in Visual Basic or in JavaScript, but by writing them using Excel's own formula language. And maybe we could have rich, nested, arbitrarily nestable data structures, arrays, records, numbers with units, probability distributions, who knows what, and make those first-class native data types in Excel. Well, that was the vision, right? So about 2000, I was first started to think about this, wrote some papers, went to visit Redmond, and here was the cycle that then ensued, right? I would go to Redmond, I would talk to them for some time. There's a whole building full of people who work on Excel. Excel is like a super tanker. It's got incredibly high value, it's got incredibly high mass, so it's hard to change its direction, but it has a remarkably small crew. And they're all really busy. But nevertheless, when I come and knock at their door, they're very friendly, and they say, "Simon, come in, have a coffee. You know, let's talk." And we do. And they, you know, I talk about user-defined functions and how great this would be, and data types, and they're very pleased. They think this would be great. And then they enter the phase of the then 3-year life cycle of Excel releases, because Excel came out in 3-year releases in a box, right? There was Excel 10, Excel 11. And they would come to the point in the life cycle where they had to decide what they were going to implement in the next release. So there was a lot of painful axing of good ideas they would like to do, but didn't have enough effort available to do. And the things that I was enthusiastic about were always the ones that got axed. So then I would go home and be a bit disappointed and wait for 1.5 years while they implemented all the stuff they were going to do until they were receptive again for the next cycle. So this is what I did. But this did not work very well because of this sort of repeatedly getting axed thing. So here is the plan that turned out to work better. But it wasn't my plan in advance. It's only my plan looking backwards. And it's this. First of all, go and make a lot of friends. So that was this sort of 8-year process of making friends with the Excel team. Then I simply went away for 7 years. Right? I sort of did other things. I think I became a bit discouraged. But then what I realized was all I had to do was wait for one of my friends to get promoted. And because I had made enough friends, One of them was promoted to be the great boss of Excel. So I contacted him in December 2012, my old friend Dave, and I said, Dave, we should do some of this stuff. It would be so good. And interestingly, this time he said, oh yeah, that would be great, Simon. We so should. And so it still took 7 years. Here we are, 7 years later. These things have started to come out because of this high mass business. But from that day, we got real engagement. It was great. But I think one of the things that made a difference, and this may be of at least academic interest to some of you, is that one of the things that made a difference is not only my friends getting promoted, but also moving from this 3-year cycle to the continuous delivery model that happens now, so software as a service, in which Microsoft puts out new features every few weeks. You know, your system pauses and says, would you like to install updates and all of that? Well, that changed perspectives, because I thought that might shorten the planning horizon to a 3-week planning horizon, but that would be silly. Everyone knew that was silly. So it actually lengthened the planning horizon, because they think, what is our grand story arc? What is our long-term arc? And then they think, what can we deliver in smaller increments? So it turned out that was also very helpful to building this larger scale change into Excel. So the story I've wanted to tell so far is just, functional programming, a completely different way of thinking about programming compared to the one that we're used to as it were, mainstream programmers, certainly the one I was used to before I went to university. Excel embodies that functional programming paradigm absolutely from the ground up, and moreover is used by millions and millions of people. Maybe we can make Excel into a true functional programming language. And that's the journey we've been on. And now Andy's going to make that a bit more tangible by showing you some of what we've actually managed to do. But first, just let's pause to see if anybody's been trying to ask a question.
There is a question in the chat, Simon. Someone was asking about why imperative programming was so popular compared to functional for a long time.
Why is imperative programming? Imperative programming why is it so popular compared to functional programming? Imperative programming is very close to what the underlying computer does. If you're programming, you know, a Z80, which is what I was doing, a Z80 is a little von Neumann machine, right? This is a von Neumann lecture. It's a little von Neumann machine, and it works by changing the states of the registers. So imperative programming is a very good fit with the core machine on which we execute. To execute a functional programming language, we have to do all this tree manipulation or something akin to that, and that takes more work. So I think there's quite a good reason why mainstream languages became embedded initially.
So even when I'm running a functional program, it first gets converted into something that will be imperative and then run, right?
Yeah. So
can we have like inherently functional?
An inherently functional machine. Yes. So while I was at Cambridge, this was all flavored. John Backus produced his Turing Award. Turing Award lecture called "Can Functional Programming be liberated from the von Neumann style?" Which is his war cry was, "Can we build machines that execute functional programs directly?" So it was a very inspiring lecture, and it gave birth to lots of bright young things like me and John Hughes and others at the time, who were all excited that a von Neumann lecture, the Turing Award lecture, was saying functional programming was the thing. But it turned out to be a terrible mistake, right? We did actually build machines. There was a machine called the SKI machine, SKIM. So grep for SKIM, or the SKI machine. It's a paper from Thomas Clark and his colleagues here at Cambridge while we were postgraduates here while we were at Cambridge, and it was about executing functional programs directly in hardware. It was microcoded. But it turns out to be much better to instead translate it by a compiler, to translate it to more traditional von Neumann machines. So the GHC, the compiler for Haskell, does exactly that. And nobody's yet built found a way to make a piece of hardware that's actually better at executing functional programs than compiling it to something that Intel's built. It's slightly surprising, perhaps, but there it is.
Yeah. May I also ask a question in this direction? So when just for context, I'm at Oxford, not right now, physically, but I'm studying at Oxford, and they have digital systems course in the first year. And they teach basically some aspects of hardware design using Haskell, like combinational circuits and so on. Can that be seen in some way as as an inherently, say, functional aspect of at least combinational circuits? Like, because at first I even had that impression that it was.
Right, because if you think of an AND gate or a combinational circuit is just the functional programming, really, isn't it? It's a data flow machine. The signals just flow through the network. When you have a register, right, that captures state and then maybe feeds it back to the beginning, then you've got to think again. So, but Haskell is a great language for modeling or describing. It's a kind of domain-specific language for describing hardware, yes. And people indeed have Satnam Singh, search for papers by Satnam Singh to look for lots of papers about, Satnam would like to directly compile Haskell into hardware, right? We'd like to say, take your Haskell program and turn it into an FPGA. And a company called Myrtlesoft do quite a bit of that too, in Cambridge, actually.
That's great, thanks a lot.
Is there any other quick questions? Then we'll move on to
I have one question.
Yeah, Zev.
So unless I misunderstand, while lambda calculus is like sort of Turing complete, any implementation of lambda calculus will have to have bounded memory because your like Excel doesn't have infinite amount of memory. So how do you take that into account when you're implementing lambda calculus, and what are the benefits of doing something that is Turing complete compared to doing something that works with bounded memory, like some finite state thing?
Oh, well, let's see, when you're in very resource constrained machines, you might well want to work with some more restricted domain specific language that guarantees to work within certain space bounds, but I think it's I don't know of any such guaranteed resource limited language that is expressive enough for general purpose programming. If you want to write a word processor or any moderately complicated application, it soon becomes painful. So it's to do with expressiveness, I think. It's that anything that isn't Turing complete tends to bite you pretty hard pretty soon in terms of the sorts of programs you can write. That's my impression.
Right. And how do you take it into account when you're preparing, like when you try to get it on Excel, how do you take into account the fact that there's a balance?
Well, so it's true that therefore any program that you write in a Turing complete language might run out of time. It might just fail to terminate, right? That's the famous halting problem, right? So it might run out of time or it might run out of space. Both are problems. And essentially we leave it, we try to give a close enough execution model that the programmer can reason about whether that's going to happen and make sure it doesn't. But real programmers spend quite a bit of time trying to reason about the space and time behavior of their programs. But it's typically not a guarantee by the compiler. I will say too that imperative programming languages tend to have simpler cost models. That is to say, it's easier to know how much space and time your program will take in an imperative programming language than it is in a functional programming language. And I take that's both a plus for imperative because it's easier to reason about the cost model, but it's a minus for imperative because I think functional programming is just higher level, right? So you have to worry about less. It's the distance from you to the machine is greater. And so of course, if you want to reason about what the machine is doing, you've got a bigger gap to jump. Good, Andy, why don't you jump in and then we can have more questions in a little while.
All right, thanks, Simon. So I'm also a functional programmer and I'm also passionate about bringing the power of functional programming to end users. And I'm particularly excited about analyzing data. And so about 10 years ago, I got into this topic called probabilistic programming that is a kind of rather innovative branch of functional programming that lets you model and analyze data and use something called Bayesian statistics to do so. And I got really excited about that. And we built a new probabilistic programming language that we called Tabular that was embedded within Excel. And the reason we did that was that we wanted to build something that end users could use to access data. And frankly, almost all the world's data that people sort of interact with, at least, in many situations anyway, lands up in spreadsheets. So we thought, right, let's take the programming language to the spreadsheet. And so we built this system and there's a screenshot there. I'm not going to talk about this at all, really. That would be a whole other talk to talk about probabilistic programming. But a key link with Simon is that we built this implementation about 5 years ago. And a lot of the limitations that Simon was talking about in Excel, that you can only have like a string or a number sitting in a cell and not compound data, and that you can't easily, write lambdas in Excel and sort of capture bits of logic, bits of, in my case, it would be capturing bits of probabilistic models of data. You'd like to be able to write that as a lambda, but you couldn't do that in Excel. So, I was like, always talking with Simon and realized that the kind of things that he was trying to do with Excel, would fit tabular perfectly. So I decided to put tabular on hold and join forces, and so here we are. So that's how I got here. But so Simon was talking about these two big ideas, and in this part of the talk, what I'm going to do is talk about how these have unfolded in the actual product over the last few years. And then I'm going to give you a bit of a deep dive on what it's like to actually program with lambdas in Excel today in the product. And you should be able to actually download Excel and switch on this feature if you've got a M36 or a Microsoft 365 subscription. And so hopefully at the end you'll be able to sort of actually play with this. But let's see, how did things go? Well, I mean, there were two parts. The first was like to introduce, compound data into cells to take Excel beyond text to numbers. And what this slide is showing is some formulas running in Excel with this concept called dynamic arrays, where we have a formula that returns an array, and then we kind of functions acting on it, and the data sort of spills out. So if we go, let's see, to here, we've got a sort function. We pass it this range, which becomes an array, and we sort it, and you get a sorted version of the whole range. And here we say unique on this whole range, and we get all the unique values with no duplicates. And here we call the filter function and give it a range and give it a predicate. So we filter for values equal veg. And in that column, we get just the corresponding names over there. So that's really cool. You've now got a single formula in one cell that writes a whole array. It puts the first element of the array into the top cell, and then it writes the other values of the array into the cells beneath it. And so now you're really programming with a whole compound structure that's spilled out of the array, out of the cell. So that's really cool, and that was pretty well received. And that was first announced back in 2018 at something called Ignite, Microsoft Ignite, which is a sort of trade show that Microsoft puts on every year to announce new features in products. So that was great. Simon, told you he'd been speaking with folks in the Excel team for a long time about introducing ideas like say lambdas and sheet-defined functions into Excel. And things have been going well, and we've been collaborating with them on the details of that. And he was talking about how he'd been going to see them. Well, also in 2018, this picture that was taken on Simon's birthday, and we got him a cake. I took the photo, and this is really cool. We've got the Excel engineers that come to visit us, which felt like a great step forward. This chap, Jeff, and this chap, Andrew, are two of the key engineers who maintain the core code. It's 35 years old, some of it, the code in Excel, and they've done amazing work in making it parallel, making it very fast. And Andrew in particular has worked on shipping lambdas. And Claudio Russo here, who was one of our colleagues in the lab here in Cambridge, he actually did the first big implementation of Lambda that's now shipped in Excel, along with actually another colleague who's not pictured here called Andrew Kennedy. So that was really exciting. That was sort of kind of bubbling away in 2018, but it does take a while for things to ship. But eventually, last December, hurrah, finally, Excels became public, and they went out early December, and people started making YouTube videos about Excel. So there are sort of YouTube influencers like this person here and this person here who make videos about cool new things that have happened in Excel. And they did that. And here's some lambdas they've been writing. So we've been like programming away in Excel with Lambda for a few years. But it was really mind-boggling to see the kind of lambdas that people were starting to write. It was very, very stimulating. So that was fantastic. And then Simon and I wrote a blog post about it, Lambda, the ultimate Excel worksheet function, which got really popular. Many people have read that. It's great. Satya Nadella, who is the CEO of Microsoft, he tweeted about it. So I think I've been told, as far as I know, this is true, that this blog post is the most read blog post in the history of the Microsoft Research blog. So Lambda and Excel somehow hit a nerve, which is fantastic. And we got a bunch of interest in various press articles. So that was fantastic. Anyway, big sort of run up. Let me actually show you Excel lambdas in action. So let me type a lambda. It's as simple as that. You can just type equals and then say lambda x plus 1. And that is a lambda. Now, watch this. I hit return, evaluate the lambda. Unfortunately, at present, lambdas can't be stored in cells, so we get this #calc error from Excel, which is a message saying that this doesn't work at the moment, but maybe in the future it will. We can still press on though. Let me go back to the lambda. Let's give it a name. So we change the formula so that it is a let, and we define the name f for the lambda, and then I go Alt-Enter to add a new line inside the formula, and then I say f of, say, 42. Okay, and tap return, 43. So we've been able to evaluate the lambda on a single number. That's great. Okay, let's make a more complicated lambda. Let me make another new line. So there's the lambda. Let's calculate Pythagoras. So let's take x and y. So we'll have two arguments. And what I can do is use a let within the body of a lambda. This is a very common thing to do, where we have some intermediate values. So we can have xx is x squared, and comma, alt return, and we put in y times y, alt return, and then we take the square root of their sum. There we go. And then we change our test to be 3, 4, and I've got a red paren that doesn't match the paren of the let because I've forgotten to put a bracket here to close the lambda, right? So the red match, see, red, so that lambda's well bracketed, I think. So let's tap return. Fantastic. So we've got a lambda running, and it's calculating the hypotenuse of the of a right-angled triangle. But we want to reuse this lambda. Let's copy it, give it a name. So we copy the whole thing, Control C for copy, escape to get out of there. We go up to formulas and to define name, and we can type in Pythagoras, and then we go here to the refers to. Now that by default that just points to the cell that we were editing, so we just carefully delete it all, put the equals in because we're defining a formula, and type Control V. So we've now defined the Pythagoras function, so let's get some data, 3 and 4 again, and in here we can say Pythag autocomplete because it's a name, and we give the two arguments in those cells. Cool. And then maybe we can have other data, maybe 5 and 12. I remember our nice round numbers to calculate. And what we can do is just drag fill this formula down like that, and we get Pythagoras applied to these data. So I've shown you how we can edit formulas with lambdas directly in the grid. A nice trick here, because we can't store lambdas in cells, is that you use a let to give your lambda as you're developing it a name, and you can apply it to some test data, and then once you're happy with your lambda, you can go to the name manager and give it a name for later use. Fantastic. So that's the core idea of what we can do with lambda today in Excel. So who's going to benefit from this? You know, Simon was speaking about the different kinds of uses of Excel as like a business tool. So meet Bonnie Nardi. This is a eminent human-computer interaction researcher, and she did sort of pioneering work going out and looking and interviewing people who used spreadsheets back in the 90s. And she coined this term, the end-user programmer. And this is when someone is programming to achieve the result of a program primarily for their own personal use rather than for public use. So a professional developer is generally writing code for other people to use, or the general public to use, and maybe that's the kind of programmers we're sort of familiar with. The people who write formulas and build up inside spreadsheets are more folks like maybe secretaries or accountants, you know, children, teachers, or scientists. People who write code to support their work or their hobbies. And one thing about these folks is they're not intrinsically interested in computers, unlike, you know, maybe the folks on this call. So when we sort of build things for end user programmers, the people who tend to use spreadsheets, we really need to bear in mind that they're not professional programmers. and they, I'm sorry to say, don't really care about Turing completeness, which has, you know, been a topic of conversation this evening. So why do they care about Lambda? Well, it's pretty simple. Lambda can really help end users reuse formulas. We've done user studies on how people use Excel, and we've found amazing things that as people are learning Excel, or even, you know, once they're quite expert at Excel, a lot of people have got like favorite formulas that they use to accomplish particular things, calculating profits or predicting how much a mortgage is going to cost or whatever. And we found actually people were using Word files you know, to remember useful formulas, and they open up Word and copy a formula out of there and drop it into the spreadsheet, which is really sad. You know, that, you know, Excel should make it easier to remember formulas, but it doesn't. But Lambda is going to be great for this. So here's an example. Here is a Lambda for calculating a conversion rate. From what, let me give an example. So you would call it like this: conversion rate from US dollars to GBP on a particular day. Now, can you do that already in Excel? Unfortunately, you can't as a built-in function. There is, though, a built-in function called stock history that is a really powerful function, like many of the things that are built into Excel. It's a really general-purpose tool, and it can give you histories of the values of many different stocks. And a currency isn't a stock, but Microsoft has sort of simulated currency conversion rates as being special stocks with funny names, which I show here. Yes, so Excel will support a string like that as a stock that represents the rate of going from one currency to the other. So what I've shown you here, that this body here, this code here, is a way to specialize this general purpose stock history function so as to calculate a conversion rate. So you could call it like this, passing in the two currencies you want to convert and a date, and they would become from, to, and today. And then we construct this string that we want to pass as string, and then we call stock history, and it would return this. It's like a general purpose thing. It gives a date, and it returns one of these spilled arrays I spoke about, right? You get a header row, and you get a date, and you get the particular price on that particular day. And we don't want all that stuff. So we have a special form that uses index, which is just looking up the second row and the second column to get this value, calling it result. And then, oh, sometimes some days don't have any conversion rates. If for example, they're at the weekend, and you get an error back from stock history. And so we catch that with if error. And so if this value is not a number, if it's an error, we'll get this string instead. And so this is the kind of formula people were saving away in Word. And now with Lambda, it's great. You can just give it a name. And so this is showing you in action where I've defined this conversion rate function, and I've just filled it down and done a lot of conversions. So this is we think is going to be one of the big hits of Lambda with end users. But let me go on. We've got arrays. So they're very powerful, and we have those built-in functions I told you about, the sort and the sort and unique functions. Well, how can we? It's actually quite difficult, though, to use those to kind of write arbitrary calculations about arrays. And a really useful function to have to build arrays now comes with Lambda, called array make, and you give it the size of the array you want to construct. So m rows and n columns, and you give it a function, and then it will calculate this array. So for example, if I call array make like this, if I have 3 rows and 4 columns, and then ask for to do this calculation, which is going to return just the sort of sequence number, you get this array back. And this is super powerful. We can do lots of stuff with array make in terms of building complicated arrays and actually programming in interesting ways. So for example, here is a function called vstack written with Lambda. Let's ignore the code for a moment. Just look on the right. This is how it works. If I call vstack with sequence 33, which is an array like that, it's got 3 rows and 3 columns. And what sequence does is it just goes 1, 2, 3, 4, 5, 6 to fill out the array. I call vstack with that, and also sequence 42, this guy, it basically just stacks them together. So you get this bigger composite array. And the way it does it is it figures out how big the 2 arrays are by calling these the rows and columns functions to get the dimensions of it. And then we call array make down here. So it's got the same number, it's got the number of rows equal to the sum of the rows in each of the 2 arrays. And the number of columns is the maximum of the 2 arrays we've pushed in, and then the lambda, which gives you the value of the ith row and the jth column, is this calculation here. And there's a bit of logic here to figure out whether we're going to be returning the top array or the bottom one, and whether or not you've got to fill in some blanks. And so, you know, we can implement VStack, which is fantastic. So what else can we do with that? I'm going to show you, well, before I get to that, so far I've shown you how we can edit lambdas by pushing them into the name manager. Turns out that that's really troublesome to do for code of any size. So our colleague, Jack Williams, who's a researcher in our lab, has built a really cool tool called a Lambda Playground, which is an add-in for Excel that lets you edit lambdas as if they are a programming language. Let me show you that in action. So here is a video where I'm going to show you how to use the lambda functions, and including array make, to do text split, which is going to break up this string into an array of the substrings that are separated by the comma.
Andy, just before you show the video, just to remind everybody that array make is interesting because it takes a lambda as its argument. Or the earlier examples really only had lambdas as you bind a name to a lambda and then you call a function with that name. Here we're passing the lambda into array make. So this is higher order functional programming in which functions can themselves be the argument to other functions. So array make is, you know, most functions take strings or text or arrays as their argument. Array make takes a function as its argument. That's also, you know, a completely new thing to do in Excel, but it's in Excel today. So, sorry, go ahead now, you can play.
The first thing we want to do is to actually turn this string into an array of single character strings. So I'll do that by calling an explode function. So I just say explode of h1. There we go. And now we've got an array that has spilled out. You can see it displaying here. It's got this slight sort of bevel around it that indicates that it's a single object that's spilling out of h2. It's defined by this function explode. You can see it's explode of h1. It's a lambda. It uses array make to build the array. Array make is called with this argument indicating the number of rows, one row, a column for each items in the string, and then each item ij, so it's row I, column j, is obtained by calling the built-in mid function to extract a string of length 1 starting at position j in the string, and hence we get this nice array. Next, we want to have a text split function that will actually break the original string up into an array of strings Amy, Felina, and Margaret. And we're going to use explode as a subroutine. So let me just scroll down and show you.
Sorry about that. I was trying to click to look at the chat.
Text split.
Okay, here we go.
All right. So let me just call it here. So I say text split of the same string. And I need to pass in a delimiter, which is going to be comma. And there we go. So what's happened? Well, what we're seeing actually is an intermediate version of the result. It actually takes 4 or 5 steps to actually calculate the array. And we begin by calling explode. And what we do is we put the delimiter comma at the start and at the end of the string, and is string concatenation in Excel. So what you get is this array here, where we have a comma at the very start, and we also arrange that at the very end there is a comma. Okay, so that's going to be handy just to mark the beginning and end of the string. We know that there's always going to be a comma in those positions. So then the next step we do is we build an array that is going to have markers in it, which would be the indexes of the where all the commas are in the in this array. So if we look at step 2, I just changed the result of the let to return 2, and you see step 2 returns an array of the indexes of the delimiters of the comma, and it's computed by this array make function here. And you can see at column J it tests to see whether the item in the original array equals the delimiter, in which case it returns j, otherwise it returns 0. So you get this kind of thing. See, that comma corresponds to the 5, the comma at the very start corresponds to that 1, and so on. And then the step after that is that we break it down to being just the those indexes. So we call the filter function. So this is a built-in function on dynamic arrays that takes an array of numbers and filters it via this test. So this becomes a column of bools, of trues and falses, and it includes only the items of this array that correspond to a true in that array. So basically we get this array here of the indexes of the commas in the string. So then step 4, we can actually build our complete result from the function by calling array make, and we use the length of starts to determine how many words. So it's one less than that in the output, and for each word we compute the start index into the word. We compute the count, which is the difference between the next index and the start minus 1, and then we just return the string by calling the mid function, which is built into Excel. And the result I can show you is here.
Okay, so that's just showing you the kind of programming we could do with dynamic arrays, kind of in some detail. We've got another example called tag view, which is a formula that will produce the table on the right. So tag view, if we give it a column, if we give it an input data structure like this on the left, and we want to reorganize it like that, sort of inverting it. This is a very common thing where people want to represent sets of values, and they do it. I've seen this today in spreadsheets. People would just use comma-separated lists like this to have sets of values, which is fine. You can see it, and people understand what you mean. You know, it's people, a group of names, people, team members who are tagged on a particular country. But Excel can't really process these as sets before Lambda. There's no functions that will act on those comma-separated strings, and you can't sort of pivot to get a table like the right. But we've got a Lambda that does that, and I won't go through the details of it at all. But it's similar calculations to the sort of stuff I've shown you earlier. So we've got a video of that, but I won't show that. So we've got this out. We got this MVP. On some level, it's Turing complete, but there are limitations. So, for example, we don't have something called tail recursion optimization, which is really important to avoid exceeding our finite stack depth. There's the standard classic functional programming combinators you might have heard of, things like map and reduce. They're coming, but they're not out yet. Although we can actually program them already using recursion in this MVP. There's various other limitations, but we're hoping to lift these in the future. And big yellow sticky note, this Lambda playground that we've seen, we're planning to put that out as an add-in that everyone can use. So it will make it a lot easier to program with Lambdas. How do we think end users will share libraries of Lambdas? Remember the kind of people that we're talking about. Secretaries, accountants, children, and so forth. What we think is that the people who will be writing these libraries of Lambdas will be a small in number, people who are pretty maybe advanced domain experts who can build libraries for particular tasks, like say probabilistic programming that I was talking about earlier that got me into this. Lots of other topics that people might build a bunch of code to solve some problems, but that will empower many others who are using Excel. That's the big hope of what we can do. And we don't yet know how we're going to be able to share Lambdas. And we've got a bunch of ideas, online workbooks, GitHub, and maybe tweets would be a way to go. So that remains to be seen. So let me just wrap up. Excel meets Lambda. It's a new beachhead for functional programming. We think a big use case is going to be reuse of complex formulas that people otherwise would write down or something, but they'll be able to now share them and reuse them using Lambda. A bit of a question about how to share libraries, but we're working on that and hoping to sort of work with the community on that. Do come join us if you'd like to try it. If you spin up desktop Excel on Mac or on PC, if you go into the sort of file area, you'll see a product information button. And if you go there, it's the kind of place where you can click on Office updates. There's something called Office Insider. If you click on that and join the beta channel, then you will get Lambdas in your copy of Excel. All right. Thanks for your attention.
I've got a question. I've got a couple, actually. As you showed in the talk earlier, Excel has had from the very first version its name mechanism, which most people would use to give names to blocks of cells on their worksheet, but can equally be used to give names to formulas. Mm. And that has long been tantalizingly close to what we're talking about here. But what it lacked was any notion of parameter passing. So yes. But on the other hand, right from the very first version, Excel had a very pretty macro language, which I seem to be the only person in the world to have liked, and which sadly has sort of got submerged by Visual Basic, but it's still there if you go and look for it. And that did have parameter passing mechanisms in it. So I'm intrigued to know how much of this stuff that was already in Excel you were able to build on in constructing this new mechanism, or whether it's been completely engineered from scratch.
Well, it doesn't build. I think I know what you mean. There's a sort of, is it Excel V5 macros you're talking about?
Well, I think they call version 4 macros, but yes.
Version 4. All right. I was off by one. Sorry. It doesn't build on that at all. What we did was take the original sort of calculation engine and extend it with new instructions to support Lambda, which required a bunch of changes in the underlying C++. But it's very much a change. It's a change at that level, and it's in the shared code base that is used for all the different versions of Excel. So we did it once in the C++, and now it's available in all the different, in Mac and in Windows.
And also, it wouldn't fit at all with the old macro language. And these lambdas are really first-class values, David. They can be passed as arguments to functions. They can be stored as returned as results. They can be combined with each other. They can be stored as elements of arrays and ultimately held in cells. They're truly first-class functional programming values. And macros never were. You could name them and call them, but they weren't first-class values. These are first-class. That's a big difference. Also, I think the macros were sort of imperative. You could do things like insert rows or something, couldn't you? So yeah, they were it was really an imperative programming language, different from the functional programming. So you essentially you could write functions, but it was in another language. Moreover, it was in another language that was even less well known than Visual Basic or JavaScript. So a completely exotic and unknown imperative language. So yeah, I'm really keen on being able to write in the same language.
It also brings a performance improvement because it's true. There's VBA, so you can write functions outside the Excel function language or formula language, in VBA or also in JavaScript. But there's quite a sort of context switch, or quite a slow context switch between the Excel calculation engine and say the VBA runtime or the JavaScript runtime. And so by writing code directly within the calculation engine, we avoid all that latency.
I have several colleagues in the audience, and we are paid by banks to work out whether spreadsheets that their lenders send them are actually correct. What thought have you given to what process people like us should go through in proving spreadsheets that are rich in Lambda functions?
Well, this is going to make your job much easier, because if you've got a formula that's been copy and pasted down a column or used, scattered in many places throughout a spreadsheet, instead of auditing each copy individually, you can now say, oh, they're calling this function, which I have audited once. Right. In fact, it's in a library that I've certified. So, but by providing a mechanism for sort of sharing code, it's vastly more robust to errors than this endless copy paste. So that said, of course, then you can. I think the challenge will then become that you can then write more ambitious programs, right? This will dramatically extend the reach of what people can do with spreadsheets. And if they can do more with spreadsheets, they will do more with spreadsheets, and that will make your life harder. But it will be, for doing the same thing, I think your life will be easier. But people will do more ambitious things, and that will make it harder again. So I anticipate that your life will be about as hard as it is now.
But also, I'll just add that techniques that work really well in functional programming for reducing errors in functions can be applied to this logic that's represented as lambdas. So we could have a type system for lambdas that could detect errors. And we could have, like, testing, like, quick check, for example, to sort of do randomized testing of functions. And we could embed assertions as well, that to assert that, the inputs have a certain form, maybe the outputs have a certain form. So there's a number of techniques like that that can now be applied to lambdas. Yeah, we're sort of very interested in reducing error in spreadsheets.
Very good, thank you.
Here's a question someone sent me. Can either of you comment on the pros and cons of being a computer science researcher in academia versus working in industry? And also whether there's a career path in industry where you get a PhD along the way?
The latter, I don't think that there's a, Microsoft, for example, along with other companies, runs sort of PhD, PhD sponsorship programs, so that the supervisors can apply for a PhD award from Microsoft. Essentially, Microsoft funds a PhD under that advisor, and they then look for a PhD student to fill it. I don't know anybody with any industrial research labs that let you get a PhD while you are working, essentially support you to get a PhD while you're working for them. Do you, Andy?
It's not super common, but it does happen. There's one of the senior leaders in our lab, actually Manuel, has got he started as a research engineer at Microsoft many years ago, and he actually enrolled in the computer lab to do a PhD while he was being a research engineer, and got his PhD that way. That's not very common.
It's not a sort of standardized pathway. It's not really a standardized pathway, is it?
No.
So it's the exception rather than the rule. But as the first part of your question, was it like working for a company rather than working in academia? It's I think it's, it's horses for courses. There's you get a lot of, so at Microsoft at least you get a lot of freedom in what you work on. They're strongly encouraged to work on things that are that are ambitious and that have some business relevance over, in the not too distant future. So just noodling away on something that interests you by yourself, not very encouraged. So a lot depends on what kind of research you want to do. On the other hand, everybody wants their work to be applied, so it can be really motivating to work on a project with a number of other people that's trying to really move the needle for millions of people in a 5-year timescale. That can be quite motivating. But of course, that means you're not quite as turned loose autonomously as you might be in academia. But I worked for many years at Glasgow University, which I loved, and UCL before that. Great. I liked both.
If you're a researcher in a company like Microsoft, it's great if the ideas you have are directly applicable to the products. But that's basically your customer is your own company. So Simon is talking about the long time it took before Excel picked up on some of these ideas, and in the meantime they kind of languished a bit. So an advantage of being in a university, if you're a researcher, is that the sort of any company, if you come up with some great ideas that you love and you get traction, then you can go and find which company would be most interested in adopting them, and not limited to the company that you work for. Or you could even form your own company to exploit them. So that's definitely an advantage of being in a university.
Yeah, thank you.
So a question along similar lines. So, Simon, you always talk about how a good thing about Haskell is that it was at least small when you worked on it, and so you could change things up without really worrying about dependencies and how this community would react. Mm-hmm. How is working on something as mainstream as Excel different from that experience?
Oh, well, yes. Of course, it's completely different. So I have no control over what happens to Excel. So unlike Haskell, and it's and changing anything is a very slow process. But on the flip side, anything that changes in Excel, like I've never had the experience of having something, something like Lambda being released, and the next day there are 30 blog posts from professionals who've worked out how to use it, and just like people don't do that when we release features in GHC. So it's very high leverage. So it's they're just completely different. I wouldn't say one's better than the other. I think maybe I'd be frustrated if I was only working on Excel because it's slow. But the advantage of working in a research lab is you get to you get to do a lot of different things.
There was a question in the chat asking whether you think Excel will still be used in 100 years' time. Do you have anything kind of to say in that?
Andy, you can answer.
Yes.
Was that your answer? Yes.
There's a law. I did say yes. There's a law about this that if you pick any technology, there's a pretty good chance. You look at how long it's been around. There's a pretty good chance it'll be around for at least that long again. And there's a name for it. Sorry, I'll need to look up in Wikipedia. So technology that's just come out, it's been around for 6 months. There's a good chance it'll be around in 6 months, but will it be around in 10 years? Maybe not. Maybe not. If something's been around for 35 years, there's a pretty good chance it'll still be around in 35 years and beyond.
I don't know about Excel, but I do think about functional programming. So I'm frequently on record as saying that I think functional programming is on this long, slow burn, right? Functional programming, when I was at Cambridge, functional programming was very geeky, very exotic, very academic, right? Only weird people did functional programming because it was plainly, completely impractical, right? If you were going to make programs that actually did things, they had to be written in Fortran or BCPL or something. But over time, functional programming has become more and more practical. That's been one of the things that I've devoted my research life to, knocking down the barriers to practical utility. So, and I think some of the things that make imperative programming difficult, like all these uncontrolled side effects, have become more pressing as problems. So the way I put it is that when the limestone of imperative programming is worn away, the granite of functional programming will be revealed underneath. Right, that's the durable thing. I think in 100 years' time, we'll all be functional programmers. But then I would say that.
In Excel.
Maybe in Excel, yeah. But one of the things that I like, because you mentioned that I do work in education too. When Excel has this proper fully composable lambda and fully nestable arrays, then it will be possible, I think, to introduce children to programming for the first time through Excel, and it'll be functional programming. So that will mean that all the pieces of my life will come together: the Microsoft bit, the functional programming bit, and the education bit in one glorious moment. That'll be then I can die happy.
Oh, Christopher, would you like to ask a question?
Sure, thanks.
Okay.
Yeah, I'm a professional imperative programmer. Have been for coming up on 20 years, I guess. And I've kind of dabbled with functional programming over the years. It's very interesting. I think I've learned Haskell on and off, not particularly recently. But one of the things I've always found is expressing something in a functional language is not always something that comes naturally. And it often feels kind of like a puzzle, like how you write a functional program to solve a problem that for an imperative program, it seems obvious to me. I wonder if that's just because of I have a lot more experience in imperative programming, or I wonder as functional programmers whether you find things come more naturally to you if you're thinking about how would I write a program to achieve X, or whether there is a sort of innate kind of trick to doing it. You have to find a trick to how you would express a particular problem functionally.
Andy?
I find it often pretty natural to express things in functional style, and that's it's very much my background. And whether, but I am not a I'm not a kind of I'm not a sort of professional programmer who spends all my time coding. So I haven't tried doing very low level coding, for example, in functional languages. But I think you can get into a sort of into the sort of declarative way of thinking in functional programming, and it comes pretty naturally.
Yeah, I think it's a good question, Chris. But I think that once you get the more functional programming you do, the more it feels natural to do that and odd to do imperative programming. So, but I think there's a significant degree to which it's not, you can move between imperative languages relatively easily. The move to functional programming from imperative or vice versa is much more of a dislocation. You have to sort of change the way you think about the world. It does involve quite a big shift of perspective, a shift of the way you think about program design. So yes, it's not an easy thing to accomplish.
I'd also say that I've never really got the hang of object-oriented programming. You know, I learned programming when I was at university in ML, yeah, I just never get Java, C#, you know, programming with classes, just so unnatural to me.
Yeah, so I wanted to ask a quick question, like on the line of what you were saying. Yeah, so basically what I wanted to ask is, like, if you consider, say, the landmarks in the history of functional programming, as you mentioned, you have Lambda calculus, say, the invention of Haskell. Do you think Lambda being a part of Excel, considering how much Excel is used, has a place along those great landmarks? Like, will it be looked back in the future as one of those great pivoting moments of functional programming?
I think too early to say. Really.
I'm going to say yes. Because look, this is Excel is functional programming in a form in which, unlike Chris, right? So Chris was asking, it seems like a weird way to write programs. In Excel, it would be odd to do anything else. You can't imagine writing Excel formulae in which you could say, you know, equals, you know, in the middle of a formula, you could add 1 to X, you know, some mutable cell somewhere. You could print something, or you could open a valve, right? So it's Excel. Its most natural mode of thought in Excel is functional, right? So so by taking that place in which you don't have to apologize for being functional, it's just the only thing you could possibly do, it's the most natural thing in the world, and making it truly a higher order functional programming language, that I think is, you know, stands a chance of being quite significant. That will you know, I think people will write the most amazing libraries of functions, ones that we've never dreamed of, and they'll implement them in Excel. And yes, Francesco will need to find a way to enable them to share libraries of functions. It's on the slide, actually, to enable them to do that. And I think we'll see an explosion of creativity by domain experts themselves, not by programmers. I mean.
Hi, Simon, and hi, Andy. In my job as a quantitative researcher, I code in a language called Q or KDB+, which is functional. And actually, when I first started using this language and I realized it's a functional language, I knew that Haskell is I think one of the most prominent functional languages. So I did a little bit of research on it, and I just compared some syntactical things, and I actually found a lot of similarities. And I happen to really enjoy this functional language for my job, for data analysis. And I know that a lot of firms, a lot of companies use QKDB+ for data analysis tasks, but I don't know of any company which uses Haskell. So I was wondering if Haskell is, I guess, suited to the problem of data analysis. If you could shed some light on why, or maybe my information is wrong, that not many industrial firms use Haskell for analyzing data.
Let's see. I think it's true that in numerical terms, not many programmers use Haskell full stop, right? It's a minority programming language. If you look for every Haskell programmer, there's probably 100 C++ programmers, for example. I don't know about KDB+ programs. I've just been looking at KDB+ while you were speaking. I didn't know it before.
Okay.
But certainly there are companies, there are people and companies who are using Haskell for database applications. And there's some quite good Haskell libraries for accessing databases and then, manipulating queries in Haskell. If you go to Hackage and search for databases, or look at the Haskell Weekly News, search for Haskell Weekly News, that has short blog posts, and if you look for those for database ones, you'll find some. So there are definitely people who do do databasey things in Haskell, but it's a lot of this is engineering, right? So it's to do anything well takes a lot of effort, and for databases you've got to be really fast. You've got to access a lot of data quickly, and that engineering effort takes takes work. And Haskell is largely dominated by volunteers rather than companies. So
okay,
I think there's a it's a slow build. I think.
I see.
There's definitely good libraries. Opali, for example, written by Tom Ellis here at Microsoft Research, in fact, as a sideline. Oh, Daniel, do you want to voice your question? The one you just typed in?
Yeah. Hello?
Yeah, hi.
Yeah. Hi, I'm just curious, like, why will these domain experts want to create these Lambda functions and share them? They already have it working on their spreadsheets. What you say there's going to be this big boom of these domain experts.
I don't think they do. They don't have it working on their spreadsheets at all. They're frustrated. They're desperately frustrated by Excel's limitations of only handling scalar data and having to copy and paste formulae. It's not working at all for them. So I think they'll want to start making their work more reusable by writing lambdas, and then they'll say, then they'll have a colleague and they say, I want you to be able to use my functions, and then maybe they'll start thinking about the show with their domain community, and then maybe they might want to start selling them, right? So I built this library of really good functions for doing, I don't know, haberdashery, fish knitting pattern computations or something, and maybe people would buy it. Why do people want to share software? They do. There's an awful lot of it about, and this will, I think, make a much broader audience be the authors.
I think it's a good question, actually, Daniel. And that's one of the things we want to do with the Lambda Playground is get it out there, and it will enable sharing of Lambda libraries. And we want to do a bit of user research and actually ask that kind of question: why is it you're sharing it? What was difficult about sharing it? What is the benefits that you see that you're getting from doing that? I would like to be quite empirical about this, and it's actually an interesting moment, because at the moment there are no lambdas in Excel that are being shared with anyone. There's barely lambdas that are being executed in Excel itself. So it's a moment when we can sort of actually watch this community, grow and hopefully thrive, or possibly not, I suppose. But I think, like Simon, I would be surprised if that happened, or there must be some impediment, because I think there's lots of motivations that it's people like to share things and so on. That's what I think. But I think as a researcher, I'm also keen to actually try to observe what is happening and actually ask, what are the different motivations? It could be that, some people are motivated by profit and really try and sell stuff, but maybe there's a lot of other people who may be motivated more altruistically. We don't really know, because it hasn't happened yet. But I'm very keen to sort of watch this language community kind of grow. I mean, there's already quite a community of people who use Excel, but I don't think there's so much of a community yet of people who are, sharing individual formulas. Could be wrong, but and I think that Lambda will make that much more viable, and it'll be interesting to watch.
I've put in the chat a link to an example of people who are sharing, formulas that do weird things for the joy of sharing them, and I think we're going to see a lot more of it.
Thanks.
Simon, you mentioned that in GHC it's kind of a slow build because it's like an open source community of developments. I don't know if this is really a quick question, I'm sorry if it isn't, but what would you say is the role of open source development in making, say, big leaps in technology, as opposed to, say, private companies that have a lot of infrastructure, or academics? What would you say is that role?
Oh, are you asking whether open source projects or sort of closed source projects are more likely to make big steps forward?
Not exactly. Like, if you consider, for example, as far as I know about the history of Haskell, it was brought about by academics, and then it became an open source project and people contributed to it.
Yeah.
But the big leap, so to say, in what was proposed came from academia. And then, say, people from other places came in there to help build it. And scale it, but say the big leap and the proposition of a new technology came from academia, and in many other cases, for example, stuff that happened in Bell Labs or is happening in Microsoft Research, it came from private companies. So would you say that the open source community is more to like help build up new technologies proposed by academia and by private sector, or would you say otherwise?
I don't know. I'm not sure I see it as being so connected with the big leap forward tend to be, you know, a kind of serendipitous combination of some smart person or group of smart people together with, you know, a moment somehow that you know that they were lucky to hit the wave, and whether that happens to be in an open source context or not, I don't know. It's if it's about how does innovation happen, I don't think it's as simple as it happens more in an open source setting or more in not an open source setting. I'm sorry, that's not a very satisfactory answer to the question there. Andy, did it resonate in any way for you? Question?
No.
No. Right. So I'm not sure we can help you very much there. Sorry.
There's a question for Francesco in the chat, and the thing I'm not sure I want to try and answer all of that, but the part at the end about programming spatially in spreadsheets having its own merits, I would say yes, definitely. You know, the spatial grid is really allows you to kind of you know, debug and develop your formulas just very conveniently. I found that from writing Lambdas, being able to put a few test cases in the grid, and then having a Lambda that controls how those tests are, you know, controls the body of the code that is being tested by all those tests, and seeing the results instantly is just an amazing experience. You know, you type a few characters in the Lambda playground, you update your Lambda, and you instantly see the response in the grid. And so I think it's very different from you know, conventional programming. This is it's a very kind of live form of programming.
Yeah, it's as if we've been talking a lot about how programming language research might influence Excel, but I think we might also see Excel influencing programming language research, because as I was tried to say in that table earlier in my talk, it's a very different programming environment, this sort of live data first, very live. And I think that might, you know, we might see, oh, actually, if you're writing, you know, even larger functional programs, that's really nice way to write programs. Maybe we should do more of that.
Right, okay. I think we should all thank the speakers. It was a really interesting talk. And yeah, at least for me, it was very fun as well to hear about how these things work in industry and how all this is done. Yeah, thanks a lot.
Great, good. It's a pleasure. Nice meeting you all.
Yeah, and
thanks for having us.
Yeah, and thank you, of course, everyone, for coming.